So we're back, and if you recall what we've done so far, it's to look at the Georgi-Glashow model, and specifically to identify symmetry broken configurations that have the charge of a magnetic monopole. And these really are electromagnetic magnetic monopoles because the SU2 or O3 gauge group really gets broken down to U1 or SU2. And it's as though we have sort of photon coming from spontaneous symmetry breaking as a massless mode in this theory. And interestingly, we discovered that the magnetic monopole has a charge that is given by a topological invariant, expressed very simply in terms of the scalar fields. Now what we want to do is estimate the mass of the monopole. What we really want to do is find a bound for the mass of the monopole. And this will be a big plus, as I discussed, because what we couldn't do with the Dirac theory of the monopole is, for instance, figure out how massive it is, because we just added some delta function source. We didn't have any way to compute that. And we'll find that interesting things happen when the bound we will now discover is saturated. So first, let's take the expression for the Hamiltonian, and recall that really the energy or the mass is given by its integral, the integral of the Hamiltonian density. And see that it's basically p squared plus v in both the gauge field and scalar sector. The momentum in the gauge field sector is the electric field. In the scalar sector, it's the derivative, the time covariant derivative of the scalar. And the potential terms for the gauge field are just b squared, right? And for the scalar, they're the square of the spatial gradient plus the potential free of any derivatives. And so we know that this is going to be greater than just e squared plus b squared plus the gradient of phi squared. Right, so that's one bound. Why is this true? It's because we really are doing all of this on R3, right? With the metric on R3, right? Which is positive definite. And so having additional pi squared and assuming that you have a positive potential means that they're really going to add to the mass. Right? So these are really positive things you've taken away. Next, we'll do a trick where we'll add and subtract b dot di phi sine theta and b dot di phi cos theta. Right? And basically, you find that you can kind of complete the squares when you do this. And when you complete the squares, you again get some positive definite quantities, right? Whereby this double line notation, I mean the norm squared in isobector space, right? So the internal space. And once again, the idea of bounds is basically look at the positive part, right? And then you know that whatever's added to the positive part has to be smaller than the sum of the positive part plus that thing, right? So here you see that this e minus di phi sine theta squared plus b minus di phi cos theta squared, those are positive. They're sum of two positive things, which means that they can only increase whatever you, like, the value of whatever you add. And so the remainder here, sine theta di phi e and cos theta di phi e dot b, are going to be smaller than the sum. And this is what we'll work with. Right, so far everything is followable. And now what I want to do is...
So we're trying to just find bounds right now for the masses.
Exactly.
Okay. And then arrive at... okay. Got it.
Great. So now let's put the Bianchi identity to use. And what I thought was that this time, I'll try and prove the statement on paper, uh, just so that we're more in touch with what's going on. So let me turn on the camera here. Okay. Okay. Great. Let's see. So you put the spotlight on this video, I'm guessing?
Yeah.
Okay, so the first statement that we want to check is how you, well, just give me a second, is how d nu of star g mu nu, how this Bianchi identity implies that the spatial divergence of B is 0. Right, so this is also the covariant one. So we could do this in two ways, right? So we'll start maybe like, let's first take a simple example of doing this in the U1 theory, where it's abelian, right? So there we just have ordinary derivatives. D nu of star f mu nu equals 0. So we'll prove it there, right? And then we will see what happens when you have a covariant derivative. Sorry about that. Let's get back to my, sorry. Well, I guess we should pause the recording. I think I'll use a slightly thicker pen size. Okay, so first question, how are we going to write this in form language? Any guesses?
We had the exercise before, right? Did we record that?
Yeah, exactly. Do you remember? Yeah, that looks better.
Yeah, expand it out in two forms, right?
Yeah, so
Expanded two forms.
yeah, exactly. So what we want to do is do it with the two form. So which two form do we care about here? We care about the field strength two form.
Yeah.
Right? And nominally, this is saying that we have star f, right? But since we're taking a contraction with the derivative, we need to use the divergence. Right? So the divergence is what? Star d star.
Right.
Equals 0. And remember that in Lorentzian signature, this is -1. In Euclidean signature, this is +1. But since there's 0 on the other side, basically, well, let's go back. Basically, this becomes df equals 0.
Yeah.
So now we have to process df equals 0, right? Remember that f can be written in the following way, right? It's e wish dt plus b as a two form. So I'll call this b hat, because it's not the vector field, it's the two form b.
Yeah.
Right? How is that two form b defined? Well, it's defined as epsilon b as a vector, right?
Yeah.
So it's defined as, this is, say it's a one form, dxj, wedge dxk.
Okay.
Right? So this is a split. And what does d do? E acting on something. Again, we want to do the space plus time split. So it's dt. So it's dt with the wedge, shouldn't forget. So does this notation make sense to you guys?
Yeah.
Which means that if I hit something with d, then this is what it does, basically.
Yeah.
It does differentiation and wedge.
Yeah.
Cool. So let's keep going. What do we have now? We have df, right?
Mm-hmm.
It's basically given by t f with dt plus, I'll call this dsf, which is basically acting by the derivatives with respect to the spatial coordinates, wedge the spatial one forms. Let's move it. Okay, that's what I mean. It's like the spatial covariant derivative. This is all review, you're right. But I just wanted to lay it out so that we know what to do when we have covariant derivatives.
Yeah.
Right. Cool. And also, we know that f splits into e dt, where again, this is a one form. And this is a two form. So you guys following so far?
Yeah.
So what happens? If I have wedge here, it's not, so it's going to give 0 when it hits this, right? Because I have dt wedge dt. So that means that this term is really only going to see contribution from here.
Right.
So is that making sense?
Yeah.
Cool. So then what we have is dt b hat wedge dt, right? Because the other terms are 0, plus ds of e wedge dt plus b hat.
Yeah.
So you see, you collect these terms, and you have some equation wedge dt plus the rest. You see, the term that involves dsb will contain no dt terms. And it's okay because you see, b has dx wedge dx, but there's 3 dimensions, like there's 3 dimensions, so you can have another dx and it'll be fine, right, in space. So this is how you sort of collect Maxwell's equations. You have dtb plus e wedge dt, right, plus ds of b hat. Now, what is this really? This is really like epsilon ijk bi dxj wedge dxk, right? And what's the effect of ds going to be?
So
ds is going to introduce another. Okay, so let's do that more carefully. Yeah, the only reason I'm expanding this is because there's a few steps which, if you haven't seen before, you might not follow and might just seem mysterious. But once you've seen it, you just apply it over and over again.
right.
So ds of b hat is ds of epsilon ijk so it's really like dk Okay, wedge. Sorry, I shouldn't call it K. I've already used K.
Yeah.
My bad. Right, so let's call it L.
Yeah.
Mm-hmm.
You see this? This is a
3,
top degree form
Yep.
in 3 dimensions, which means that it's epsilon JKL times the volume form. By this, I mean, like if we were on a curved space, it would be a square root G d3x. So dx0, which dx1, which dx2. In some sense, there's just 1, 3 form. Right. Cool. So now,
Just like
yeah.
just a question, a tangential question. Does the metric determinant, does it have anything to do with the B?
Not really.
No, it's
I mean,
because epsilon is really the densitized epsilon. I mean, if you're doing this on a curved space, you're trying to obtain a volume element, and the volume element always involves a determinant of the metric.
Yeah.
okay. Cool.
But for now, let's just ignore that because we're on flat space. So what do we have here? We have epsilon I, j, k, epsilon j, k, l, dl, pi, and that's the volume element, which is just this is just delta I, j. This is why the Bianchi identity df equals 0 implies the divergence of the electromagnetic magnetic field really, sorry, I should call this EM, is 0. Okay, cool. Now, what we have is not really electromagnetism, but SU2 gauge theory, right? We had a statement that looked like this, that looked like d mu star g mu equals 0. Now, instead of using the exterior derivative, when you have a covariant derivative, you can use what's called the covariant exterior derivative, which has many of the same properties as the exterior derivative, right? So this statement can just be written as star g star d sub w star equals 0. Right, so basically, sorry about that, the action, I should explain that the action of d sub w on something is given by d mu, something wedge dx mu. So again, this implies that dw g equals 0.
The same, yeah, exercise.
Great. So now we run through the steps, right? And we write g. So nothing prevents us. Remember, this is an isovector. I mean, nothing prevents us from doing all the steps that we did before, right? So from splitting this up into E, now there's sort of 3 electric and magnetic fields because this is an O3 theory. I keep saying SU2, but I mean O3 because of our conventions. This is E which dt plus, I'll call this is bad notation, I know, but you know what this means now. This is like b hat epsilon I jk exchange xk.
Yeah.
That's what this means. And then what we're going to get are, this is going to split into 2 equations. One involving dT b equals stuff. We don't care about that one. The other one is going to be dWs of B equals 0.
Yeah.
Okay.
So are you wondering about something, Pratyut? You're confused.
No, I'm just like wondering how the DW splits into S and T.
The same as what we saw.
Yeah, good. Okay, then let's explain that too. Oh, sorry about that. You see, this is a 4-vector index, so it's got a 0 component and an I component, right?
Okay.
So that means that I have d0 of something,
Okay.
dt, plus I, dxi.
Right.
Cool. And this now means that the covariant divergence of B is 0. Right. So this is like, which then takes us back to our slide. Right? And show that that just leads you to a boundary term when you do the integral. Right? So divergence of star D is 0, which means the divergence of B covariantly is 0, which furthermore, when you take it through here, right, gives you sort of a vanishing contribution. The extra one is vanishing, you'll just get the total divergence, and you'll get basically phi dot B, the integration of phi dot B, which is nothing but the integral of the electromagnetic B, the surface integral of the electromagnetic B, which is the magnetic flux. Cool. So the next thing is going to be an equation of motion. Right? So now let's do the exercise again so that we can check that we're going to have the divergence of E being 0. So stop the shares, the screen share. And I'll start. Okay, so I'll just let it come into focus. Okay. So, well, the statement here was that d mu equaled, so it's like a phi plus d mu of phi. So let's now bear in mind that outside the monopole's core, we have the Higgs vacuum condition. Right, so this is 0 outside the core. So at large distances, we have the Higgs vacuum condition that sets this term to 0. Right?
Yeah.
So then we have to process what we have here. And what is this going to be in form notation? I mean, these are good exercises just because they sort of, exercise both kinds of terms. So you see, whenever you have a contraction, you have to involve the hot stuff, right? And when you take the divergence, you're really using a different differential, which is the causal differential, which you can write as star dw star.
Yeah.
There's this vector indices and everything. G equals C.
Okay.
Now we have to split this guy. So is our lesson. We have star of E dt plus this funny B2 form. Let's write that more explicitly. E dt plus cool. And so this will take you to minus of epsilon 0 So I have 4 and I have
Oh, right. Yeah.
right, just for dt. But note that we really have a 2 form here.
Right.
This is a 3 form. So it's not enough to know that. So really, if we collect our form indices, then what do we have? We have dxi wedge dt.
Yeah.
And then under star, that will go to what? That will go to epsilon 0I jk dxj wedge dxk.
Yeah, that makes sense.
Which we can write in terms of 3-dimensional epsilon cool. And same thing here. So you see, this is basically, this is going to all be under star. It's going to go to minus dxi wedge dt.
Yeah.
So great. We're going to have epsilon I jk e I dxj wedge dxk plus, oh, sorry, minus, getting that wrong, bi, well, this looks like a very odd b. I'm just trying to avoid the close button here at the very bottom. Great, so this is your electromagnetic duality in action. Great, so now what we're going to take is W of epsilon I j ei okay. And we remember all of our steps. See, immediately this is going to vanish because this dt was dt. Right? And then I'm going to have another. So let's call it L.
Right. Yeah.
right? And now we're uninterested in this equation,
Wait.
the equation involving
Why do we have
d0 of e.
dxl at the end? I must have missed something.
Sorry.
Why do we have a dxl at the end and the covariant?
So we have dl
Yeah, and the end
of the form wedge dxl.
Oh, right. Okay. Okay.
Right.
Yeah. Yeah. Okay. Yeah. Okay. Got
Cool.
it.
Cool.
Yeah.
So now, what are we going to do? So we have, you see, this is an equation we're not interested in, although it's an equation that's there, right?
Yeah.
So our remainder is going to be this equation.
Yeah.
Right.
Mm-hmm.
So now let's also take a closer look at what's going on in these flux expressions. I went over that a bit quickly with the magnetic field case, but with this case, I mean, I'm satisfied with just getting to the bound today. You know,
Yeah.
just so that we know what we're doing. So the idea was that you had the phi, right, dotted E.
Yeah.
So this is EI di phi. So I can write this as di of phi dot E phi dot right DIEI. And if I know this is 0, then I just have to process this term,
Mm-hmm.
which is sort of the idea here. Right? And basically that's where we're getting the boundary term from. So that you see this is what you're integrating the x dot e. Right? This still has an index I. And then once I use Stokes' theorem, well, before I do that, I split this up. I'm going to have pi plus, what's the rest going to be? Well, plus nothing.
There's nothing. Right? Yeah.
Because I have phi dot e, right? The sort of vector indices, the internal vector indices are dotted.
Yeah.
So it's like I'm taking a covariant derivative of a scalar in the internal space.
Yeah.
So it's just nothing.
Yeah.
That's why it's just the sort of spatial divergence, right?
Yeah.
And that's why I can write this as 2x and phi dot ei. And then this is really the electromagnetic electric field.
Mm-hmm.
Right? It's going to give me like A times E.
Yeah.
Okay.
Cool.
Right. So. Yeah.
So now I'll start. Let's go back to my slides here. Well, I called it E on the paper, but it's Q here. But you get what I mean. I'm using Gauss's law again.
Mm-hmm.
Really cool. So you see, we started with these two terms, right? That had sine theta di phi dot A and cos theta di phi dot B.
Yeah.
And then we moved to using the Bianchi identity and using, like, let's get this out. Don't think we'll need it anymore. Using the equations of motion, we get these two, right? And so finally we get a bound written in terms of just the charges. And when do you think this will be the sharpest?
When they're
Well,
orthogonal to each other. When they're exactly orthogonal to each other.
well,
The,
I mean, it's just one angle here, right?
Yeah.
So I want them to be like, I want like q cos theta to equal g sin theta.
Right.
Because neither will then, that's like when this is, you have two terms that are just adding, right? They're both appreciable.
Yeah.
Right? And that just implies that tan is q over g. Right? So if tan is q over g, you can work back to what sine and cos have to be.
Yeah.
And so finally, we get the bound that m has to be greater than a times the square root of q squared plus g squared. This is the BPS bound. Right? And so then we could ask, okay, how do you saturate the bound? Well, you saturate it when sine is 0 and cos is plus or minus 1.
Yeah.
Right? That's when you get the equality.
Yeah.
And furthermore, later we'll see it's useful to consider a static solution for which the momenta vanish, which means you only have a magnetic field, and the magnetic field has to be given by di dot phi, the di of phi. And this is called the BPS monopole. Now, right?
Okay. Yeah.
So now let's look at how you get this from just field theory, and I take this from Z's textbook. So he used a different way of deriving this bound, which doesn't involve throwing away the potential until the very end, but basically you just say that here's your mass, put e squared and b squared into this GG term, because that's what it is. And you rewrite g squared plus di phi squared. Like you rewrite that by adding and subtracting epsilon d phi. Right?
Okay.
And
what are you trying to do?
Again, you're completing this.
Okay, completing this.
Well, it's the same kind of trick. It's the same kind of trick. You want to complete the square and have a remainder.
Okay.
The remainder now is going to involve v and this g dot d phi, like epsilon g dot d phi term.
Right.
And so when v is 0 and when g equals epsilon d phi, the bound is saturated, and that gives you b equals di phi. So let's see how that works. Right? Okay, so first of all, okay, you see why the bound works. It's the same logic as what we had before.
Yeah.
You just have to complete a square and sort of set it. Cool. And further, we want to ask, when would you see the equality? And that's basically like taking sort of, okay, let's see if we can see how to saturate it also from the expression that we have here. If g equals this epsilon dk, then it's just a way of rewriting the expression, right? Let's see if that works. So first, let's drop v, and then ask, if you have zero potential, how can the bottom expression equal the top expression? And that'll only happen if g is d phi.
Right.
Because then you'd have both these terms being the same.
Yeah.
Essentially.
Yeah.
Right, so that special configuration will be equal to the mass itself.
Hmm.
And so that's the solution that saturates the bound. That happens when P is di5. So remember, the spatial components of G are the like epsilon times B, like epsilon dotted into B. So when there's an extra epsilon, that just gets rid of that first epsilon, you just have B. So see, B is just this dk phi or di phi.
Hmm.
So this is the BPS monopole. But you see, we did something weird. We said D has to be 0. And actually, that's something to be careful about. Really, to have non-zero magnetic charge and have D 0, you need lambda to vanish. You need to have like very coupling. Because otherwise, you have the Higgs vacuum condition that sort of ruins it for you.
Right.
The vacuum conditions imply that phi dot di phi is 0, and then if D is di phi, then well, phi dot D is 0. Right? So it can have non-zero magnetic charge. So you need to be careful about the order limits and how you get this thing. So this is something we will meditate on in the future, like this BPS monopole.
Hmm.
And BPS stands for Bokomoni, Prasad, and Sommerfeld. And we'll meet them many more times, especially when it comes to supersymmetric theories.
Right.
And so next time what we'll do is look at the electromagnetic duality and in this model, and look at what happens when you include an axion, a theta term.
Hmm. Right.
It might be fun if more people join us then. So for now, I guess we'll sign off.
Do you have anything before we end the job?
Nothing.
Okay. Well, I'll stop the recording then.